Deep beneath the earth, entire cities once lived and breathed. The air they shared was not a given, but a masterpiece of forgotten engineering. By the end of this journey, you will understand the precise, brilliant principles that kept thousands alive in a world of solid stone. How did ancient builders solve the puzzle of ventilation without any modern tools? What hidden systems moved fresh air through miles of darkness? The answers reveal a level of ingenuity that rivals our own. What does it truly mean to build a civilization not just on the land, but within it? The decision to carve a life from solid rock was never a casual one. It was a profound response to the world above, a world that could turn hostile in an instant. For the people of ancient Cappadocia, in what is now Turkey, the soft volcanic tuff of their landscape offered more than just building material, it offered sanctuary. Above ground, empires clashed, armies marched, and the sun could scorch the earth. But below, an entire city could vanish from sight. Derinkuyu, perhaps the most famous of these subterranean complexes, was not a simple hiding place. It was a meticulously planned refuge capable of sheltering as many as 20,000 individuals, complete with stables, churches, and storage rooms that reached depths of 280 feet. The motivation was pure survival. When scouts signaled an approaching threat, entire communities could descend, sealing themselves behind massive, wheel-shaped stone doors. Yet therein lay the paradox of their safety. In shutting out the world, they risked shutting in a slow, silent danger, the very air turning stale and lifeless. A refuge that cannot be breathed in is no refuge at all. This was the non-negotiable equation of underground life. Protection demanded isolation, but life demanded connection, a constant, invisible thread to the world above. Every person, every animal, every flickering lamp consumed precious oxygen and produced waste. Without a deliberate, engineered solution, the greatest fortress would become a tomb within days. So the challenge became breathtakingly clear. How do you design a city that breathes? How do you create lungs for a world of stone? The answer lies not in a single miraculous invention, but in the clever application of principles so fundamental they are woven into the fabric of our natural world. To see them, we must look at the first and most vital system these ancient engineers mastered, the simple, powerful physics of moving air. The solution began with a truth as old as fire itself: warm air rises. This simple, observable fact of nature became the foundational principle for every breath taken in the depths. Ancient engineers did not fight this law, they invited it in and built their cities around it. They understood that to make air move, you must give it a reason to travel, a path to follow, and a difference in pressure to propel it. This is the stack effect, sometimes called the chimney effect, and it is a force of nature they learned to conduct like a symphony. Within the still, cool rock of an underground city, the heat generated by human bodies, cooking fires, and oil lamps created pockets of warmer air. That air, now less dense, naturally wanted to ascend. The engineer's brilliance was in providing a dedicated escape route. They carved tall, narrow vertical shafts that pierced upward through multiple levels, finally opening to the surface, often disguised among the rocky landscape above. These were not just holes, they were carefully engineered exhaust channels. As the warm, stale air streamed up and out of these chimneys, it created a subtle vacuum below. Nature, abhorring a vacuum, rushed to fill it. Cooler, denser fresh air was pulled in from the surface through lower entrances, from dedicated intake tunnels carved at a downward slope, or from cleverly positioned vents facing the prevailing wind. This created a continuous, silent cycle of renewal, a passive lung for the stone city that required no fuel, no moving parts, and no oversight. It worked in the dead of night while people slept, and during the long days of a siege when the world above was silent. The system's elegance is its profound simplicity. It turns the very act of living, the heat of a community, into the engine that sustains it. This was not technology imposed upon the environment, but a dialogue with it. By understanding and channeling these natural differentials, ancient builders solved the most critical puzzle of subterranean life with nothing but observation, stone tools, and impeccable logic. It is a principle so effective that it still guides modern sustainable architecture, where buildings are designed to breathe using these same ancient rules of physics. Yet, while the stack effect formed the steady heartbeat of ventilation, it was only the first part of a more intricate system. For air to truly serve a sprawling, multi-level city, it had to do more than just move in and out. It had to be directed, distributed, and controlled. But a shaft is more than just a vertical tunnel. It is an instrument, and like any instrument, its design determines the quality of its performance. The ancient builders understood this intimately. They moved beyond simply allowing air to move and began to conduct its very journey, turning a natural phenomenon into a precise engineering system. The strategic design of these air shafts was where physics met meticulous craftsmanship. These were not random holes punched through rock. They were carefully calculated constructions, each dimension a deliberate choice. A shaft that was too wide would allow air to move too slowly, becoming stagnant in its own space. One that was too narrow might restrict the flow entirely. The solution was often a narrow, deep cylinder, a form that accelerates the air moving through it, much like placing your thumb over the end of a garden hose increases the velocity of the water. This increased speed helped pull stale air upward more efficiently and created a stronger suction to draw fresh air in from below. But the genius did not stop at the shape. The placement of these shafts was a masterclass in subterranean urban planning. Builders mapped the complex geometry of their underground cities with the flow of air in mind. They positioned intake shafts to face the direction of prevailing surface winds, turning the weather itself into a silent pump. Inside the labyrinth, shafts were placed to create specific pressure zones, ensuring that fresh air was pulled through living quarters, workshops, and communal spaces before being exhausted upward. This required an almost intuitive understanding of how air would behave in a three-dimensional stone maze, a testament to generations of accumulated knowledge. Some of these vital airways were ingeniously disguised, doubling as dry wells or hidden escape passages. A shaft might appear to be nothing more than a deep cistern for collecting water, yet its true purpose was to breathe for the levels below. This duality served a critical function. It maintained the city's ultimate secrecy and security. An invading force on the surface would see a well, not a ventilation port, leaving the hidden city's lifeline intact. Even the lining of the shafts was considered. Smoother walls reduced friction, allowing air to travel with less resistance, while rough, unfinished rock could disrupt the flow. Every variable, from diameter and depth to orientation and surface texture, was a piece of a larger puzzle, all optimized for one silent, continuous purpose: to sustain life. This level of consideration reveals something profound. These were not desperate people digging holes for air. They were sophisticated planners designing the respiratory system for a stone giant. They thought in terms of networks, pressures, and efficiencies, concepts we associate with modern mechanical engineering, yet achieved with nothing but chisels, hammers, and a profound observation of the natural world. With this intricate web of airways established, a new challenge emerged, one of delicate balance. How do you control this invisible river? How do you prevent a well-ventilated city from becoming a windswept cavern, or shut out the world during an attack without suffocating? The answer lies in the final, brilliant layer of their design, the art of precision control. Derinkuyu is where theory becomes breathtaking reality, a city carved not just into the earth, but into the very principles of air itself. To walk its restored passages today is to witness an ancient blueprint for survival, executed on a staggering scale. This was not a single shelter, but a vertical metropolis descending nearly 200 feet through 18 distinct levels, a depth that would challenge even modern engineering. At this scale, the simple stack effect needed orchestration. The builders achieved this with a network of over 50 ventilation shafts, each one a lifeline drilled with painstaking precision from the surface down to the deepest chambers. Imagine the effort, carving through solid rock not just to create space, but to create breath, ensuring that a family on the bottom floor had the same access to fresh air as those near the top. These shafts were masterpieces of multi-purpose design. Many were integrated directly with the city's vital water wells. This was a stroke of genius that served two critical functions. First, it disguised the shafts from the surface, protecting the city's secret. Second, and more importantly, it protected the water supply. By channeling air intake through these dedicated stone tubes, the engineers prevented contaminants from the living areas, dust or smoke, from falling into and polluting the precious drinking water below. Every element was considered in relation to another, a holistic approach to underground habitability. The city's internal architecture further reveals this sophisticated understanding of airflow. The corridors are often narrow and winding, creating natural channels that guide and accelerate the incoming air. Then, these passages suddenly open into large, expansive rooms, like communal halls or stables. This was a deliberate pressure management system. As air moves from a tight space into a large one, it slows down and expands. This change prevents drafts from becoming howling winds in the living quarters, allowing the fresh air to gently disperse and mix, effectively bathing the entire room. Conversely, the design helped pull stale air from these large chambers back into the narrower exhaust channels, where it would accelerate upward and out. This careful manipulation of space, of constriction and expansion, acted like a natural pump and diffuser, ensuring no corner of the city, no matter how remote, suffered from stagnant, lifeless air. It transformed the entire rock mass into a dynamic respiratory system. Derinkuyu stands as a monumental testament. It proves that with observation, patience, and brilliant design, a community could thrive in profound darkness, connected to the world above by nothing but an invisible, engineered breeze. This achievement moves beyond mere shelter. It represents a complete reimagining of what a city could be. Yet, even with perfect air, another fundamental human need remained, one just as vital for a hidden civilization hoping to outlast a siege: the need for light in the endless dark. The very layout of these underground cities reveals a profound truth, that survival was a communal act and the air they breathed was a shared resource. Beyond the shafts and tunnels, the social architecture itself became an integral part of the ventilation system. Large communal spaces were not just centers of community life, they were the beating hearts of the city's environmental design. Places of gathering like churches, meeting halls, and the stables that housed essential livestock were often strategically positioned adjacent to major air shafts. This placement was no accident. When a community came together for a ceremony, a meeting, or to tend the animals, the collective body heat generated by people and beasts created a powerful thermal plume. This localized warmth supercharged the stack effect right at its source, acting like a gentle bellows that pulled cooler, fresh air more vigorously through the intake tunnels and pushed the stale air upward and out. The hall itself became a living lung, its social function directly powering the physical system that sustained it. This interconnected thinking extended to every carved room and corridor. The typical underground city was a web of connectivity. Living quarters, storage rooms, workshops, and wine presses were all linked by a network of passages that allowed for both movement and airflow. This design prevented the creation of isolated, dead-end pockets where air could grow stagnant and dangerous. Instead, it ensured that the fresh air drawn into the complex could circulate, permeating every functional space before being exhausted. A breath taken in a deep-level storage room had likely traveled past a family's living area and a communal kitchen, picking up warmth and moisture along the way, which only helped to fuel its eventual upward journey. This was a closed-loop system of astonishing efficiency, where human activity and architectural planning were in constant, silent dialogue. What emerges from this is a holistic vision of survival, where every aspect of life, from where people worshipped to where they stored their grain, was considered part of a single, integrated life support system. The engineering was not separate from the society, it was its foundation. The need for community strengthened the engineering, and the clever engineering, in turn, protected the community. This seamless fusion of social structure and environmental mastery hints at a sophisticated understanding that our modern world often segments into separate disciplines. It makes you wonder, in our own quest for sustainable living, what fundamental connections between how we live and how we build have we forgotten? Yet, even with fresh air circulating and communities gathered, one primal challenge remained for a civilization living in eternal night. How do you push back the darkness without poisoning the very air you worked so hard to purify? The stone surrounding these cities was far from a passive barrier. It was a living, breathing partner in their survival. This brings us to the third, often overlooked principle of their design: temperature regulation through thermal mass. The Earth itself possesses an incredible ability to absorb, store, and slowly release heat, a property known as thermal mass. The sheer volume of rock encapsulating a city like Derinkuyu acted as a colossal thermal battery. While the surface world baked under a summer sun or froze in winter winds, the deep underground remained in a remarkably stable temperature range, often hovering around a cool, consistent 50 to 55 degrees Fahrenheit. This stability was not just about comfort, it was the bedrock of their entire ventilation strategy. Remember, the stack effect relies on a temperature difference between the inside and outside air. If the underground city's temperature fluctuated wildly with the seasons, the airflow would become unpredictable, surging in some conditions and stalling in others. The thermal mass of the Earth provided that crucial, steady baseline. It ensured that the warm air generated by inhabitants and fires always had a significantly cooler mass of surrounding rock to contrast against, guaranteeing the upward pull of the chimney effect would work reliably, day after day, season after season. The rock didn't just house the system, it powered its consistency. But the ancient engineers did not stop at merely benefiting from this natural stability. They actively manipulated it. In some sophisticated complexes, you can find evidence of air preconditioning tunnels. These were longer, winding intake passages carved through the rock before the fresh air reached the main living areas. The concept is brilliantly simple. In the heat of summer, surface air would be warmed. As it traveled through these cooler subterranean channels, the surrounding rock would gently draw the heat out, delivering air that was not just fresh, but refreshingly cool to the inhabitants below. Conversely, in the depths of winter, frigid surface air would enter these same tunnels and gradually absorb a slight amount of geothermal warmth from the Earth, taking the biting edge off the cold before it swept into communal spaces. This was climate control engineered with nothing but geometry and an intuitive grasp of geothermal energy. They were using the planet's own steady temperature to refine the quality of their air, turning a potential challenge, the isolation from surface weather, into a profound sustainable advantage. This level of environmental tuning reveals a mindset that viewed the entire subterranean ecosystem as an integrated whole. Air, temperature, rock, and human activity were not separate concerns, but interlocking parts of a single life-supporting machine. It makes you realize their achievement was not just architectural, it was deeply ecological. They learned to listen to the whispers of the earth and designed a civilization that could harmonize with its rhythms. Yet, even with perfectly tempered air flowing through a stable, breathable city, one relentless element of the surface world still had to be addressed underground: the absolute consuming darkness. Light in the darkness was not provided by flame alone, but by the reflective shimmer of water. This brings us to a vital, often unseen partner in the underground city's delicate ecosystem: its water management. In these stone worlds, the systems for air and water were not separate concerns. They were two sides of the same life-giving coin, engineered in a brilliant, symbiotic dance. The deep, hand-carved wells that provided precious drinking water served a second, equally critical purpose. Each well was, in essence, a ready-made vertical shaft plunging straight down through the rock. While its primary function was to reach the aquifer, this deep bore naturally became a conduit for air exchange. The cool, damp air within the well shaft could interact with the warmer air of the living quarters, creating subtle local currents that aided the larger ventilation cycle. It was a perfect example of ancient multi-purpose design, where a single immense effort, the excavation of a well, yielded two indispensable resources: water and a pathway for air. But the relationship went deeper than just shared infrastructure. The presence of water itself actively improved the quality of the underground atmosphere. In the dry, static air of a deep cavern, evaporation from reservoirs, cisterns, and even slow-seeping underground streams performed a natural service. This evaporation added crucial moisture to the incoming air, a process known as passive humidification. For the inhabitants, this meant the air they breathed was less likely to parch their throats and irritate their lungs, a small but significant boost to comfort and health during long periods of confinement. In some designs, incoming air tunnels were deliberately routed past or over water sources, allowing the dry surface air to pick up this moisture and be gently cooled by the water's lower temperature before entering the main living areas. This was early air conditioning, achieved through nothing but clever routing and an understanding of evaporation. Yet this intimate partnership was a double-edged sword. Water in the wrong place could cripple the entire ventilation system. Ensuring that the dedicated air shafts remained dry was a constant, critical challenge. A shaft that became damp or flooded from surface runoff or groundwater seepage risked more than just blockage. The moisture could promote the growth of molds or weaken the surrounding rock, potentially leading to a catastrophic collapse. Engineers went to great lengths to protect these airways. They often lined shafts with stone or mortar to create a smoother, more water-resistant interior. The surface openings were carefully designed with raised lips or subtle grading to divert rainwater away. The placement of shafts was meticulously planned considering the water table and the flow of subsurface moisture. This ongoing battle to keep the airways clear underscores a fundamental truth of their engineering. Every system was interdependent. A failure in water management could lead directly to a failure in air supply. This seamless integration of hydrology and pneumatics, the science of water and the movement of air, reveals the holistic genius of these builders. They did not see a city as a collection of isolated problems to be solved, but as a single, living organism. Every resource, every carved space had to serve multiple, interconnected purposes for the community's survival. The well was not just a source of drink, it was a cooling tower. The air shaft was not just a vent, it was a dehumidifier. In weaving these systems together, they created a resilience that was far greater than the sum of its parts. This profound interconnection leads us to the ultimate test of their design, not in the steady rhythms of daily life, but in the frantic, sealed silence of a true emergency. Fresh air is not always clean air. For a civilization hidden beneath the earth, the very act of drawing a breath from the surface world introduced a new layer of risk. Dust, smoke from distant fires, pollen, and invisible particles could all ride the incoming breeze into the heart of the city. Historical evidence suggests that ancient engineers recognized this invisible threat and developed primitive, yet remarkably effective, methods of air filtration and purification. Their solutions were elegant extensions of the natural materials around them. At strategic air intake points where surface tunnels met the inner chambers, builders may have placed layered filters. Imagine a series of stacked stone gratings or woven reed mats, each holding a different medium. Coarse gravel would catch larger debris, followed by finer sand, and then a layer of charcoal. Charcoal, with its vast network of microscopic pores, is a powerful absorbent capable of trapping dust, certain pollutants, and even neutralizing some odors. In regions rich in volcanic rock, they might have utilized specific porous stones like tuff or pumice, materials that naturally filter particles as air passes through their labyrinthine structure. This was not a perfect HEPA filter, but it was a deliberate, thoughtful attempt to scrub the incoming air, to make it not just fresh, but safer to breathe for thousands of people over long periods. The architecture itself often served as a passive filtration system. The long, winding, downward-sloping entrance tunnels common to many underground cities were not merely for stealth or structural stability. These serpentine pathways forced incoming air to slow down, to navigate turns and changes in elevation. As the air's velocity dropped, heavier particles like dust and sand simply lost the energy to stay aloft, settling onto the tunnel floor before ever reaching the living quarters. These corridors acted as massive, natural sediment traps, a first line of defense that required no maintenance beyond occasional sweeping. What does this tell us? It reveals an awareness of environmental health that goes far beyond the basic mechanics of moving air. It shows a community thinking proactively about the quality of their shared atmosphere, about preventing illness and discomfort that could arise from prolonged exposure to airborne irritants. They understood that survival meant more than just quantity of air. It demanded a concern for its quality. This early grasp of purification principles connects their ancient struggle directly to our modern concerns about clean air and public health. It was a quiet, continuous form of care engineered into the very stone, a testament to a civilization that planned not just for the immediate threat of invasion, but for the long-term well-being of every breath taken in the dark. Yet, with clean air flowing through a stable, temperate city, one final and formidable test remained for their ingenious systems, the ultimate stress test that occurred when the massive stone doors finally rolled shut. The stone city's blueprint was its first and most profound ventilation manual. Beyond the grand shafts and tunnels, the architects sculpted the very interior with an invisible current in mind, turning everyday spaces into instruments of airflow. Doorways tell a silent story of this control. They were rarely carved in a straight, aligned sequence from one room to the next. Instead, builders intentionally offset them, creating a subtle zigzag pattern through the corridors. This was a deliberate airlock system. A direct, open hallway would allow a rushing draft to sweep from one end of the city to the other, carrying precious warmth and moisture away with it. But an offset doorway forces the moving air to slow, to turn a corner, to lose some of its momentum. This simple architectural trick prevented the uncontrolled loss of conditioned air, allowing the community to manage the breeze, not be victimized by it. It meant a family in their living quarters could enjoy a gentle circulation without a constant, chilling wind tunneling through their home. The shape of the space above them was equally considered. While many ceilings were flat out of necessity, in larger communal rooms or critical passageways, you often find evidence of curved ceilings or vaulted arches. This was not merely an aesthetic choice. A curved surface is a guide. It helps channel airflow along a specific, predictable path, much like the arched ceiling of a cathedral directs sound. This design minimized dead zones, those stagnant corners where air could pool and grow stale, ensuring the invisible river of fresh air washed against every wall. Even the smallest sources of heat became tools in this grand design. The placement of an oil lamp on a shelf or a fire pit in a communal kitchen was rarely arbitrary. Builders understood that heat creates convection, a local rising current. By positioning these heat sources strategically, perhaps near a lower vent or beneath the opening of a smaller exhaust channel, they could create a miniature, dedicated airflow system for a particular room. The lamp did not just push back the darkness, it gently stirred the air around it, helping to lift fumes and moisture upward and away from the breathing zone of the people below. This reveals the breathtaking depth of their planning. Ventilation was not an afterthought, a system added once the rooms were carved. It was the first thought, baked into the very blueprint. Every decision, from the angle of a corridor to the height of a ceiling, from the twist in a doorway to the spot where a fire would burn, was a calculated choice in the grand design of a breathable world. The city itself was a machine for living, and its moving parts were made of air and stone. This holistic mastery leads us to a final, haunting question, one that connects their silent achievement directly to our own modern world. What happens when the principles that sustained a hidden city are forgotten, and the air we depend on becomes a threat instead of a promise? The stone itself whispered the rules of its own engineering. Across the ancient world, the brilliant principles of subterranean ventilation were never applied as a rigid formula, but as a dynamic conversation with the local earth. The solutions were masterfully adapted, revealing that the true genius lay in listening to the geology and responding with breathtaking resourcefulness. Consider the soft, almost chalky volcanic tuff of Cappadocia. This material, formed from compacted volcanic ash, was a carver's dream. It was firm enough to hold the shape of vast, multi-level cities, yet soft enough to be worked with simple bronze and iron tools. This forgiving stone allowed for a strategy of precision and proliferation. Engineers could carve numerous, narrow ventilation shafts with relative ease, creating a dense, capillary-like network that reached every chamber. The ability to make many smaller vents provided redundancy and fine-tuned control over airflow in different city sections. It was a luxury of material that enabled a masterpiece of design. But what happened when the Earth presented a harder, more defiant face? In regions built from dense limestone or unyielding granite, the equation changed entirely. Carving a single vertical shaft through such rock was a monumental task, consuming vast time and labor. Here, ancient builders demonstrated incredible adaptability. They often shifted their strategy from many small vents to fewer, but much larger primary shafts. These became monumental feats of excavation, central lifelines that served entire complexes. To supplement them, engineers became experts in reading the natural landscape. They would integrate pre-existing natural fissures, caves, and sinkholes into their ventilation plans, turning the land's own weaknesses into structured airways. A network might use one or two painstakingly carved main shafts, connected to a web of tunnels that fed off and vented into natural cavern systems. This was engineering not through domination of the material, but through intelligent collaboration with it. Beyond the ease of carving, the very substance of the rock played a role in the atmosphere. The porosity of the material, its microscopic breath, became a subtle partner. Volcanic tuff and some sandstones are naturally porous. While not enough to sustain life on their own, these stones allowed for a slow, passive exchange of gases between the underground spaces and the surrounding earth. This microdiffusion could help equalize pressures and prevent the buildup of trace gases, acting as a gentle background supplement to the main mechanical airflow. In contrast, the non-porous, dense crystalline structure of granite created a perfectly sealed environment. This demanded a more rigorous, entirely engineered ventilation solution, as the air inside had no natural escape except through the designed shafts. The rock's character dictated the necessary level of human intervention. This geographical adaptability is perhaps the most profound lesson. It underscores that these were not rote constructions, but deeply observant, localized acts of creation. The engineers did not arrive with a single blueprint. They arrived with a set of principles and a keen eye. They assessed the stone's hardness, its fractures, its permeability, and then asked, how can we make this specific mountain breathe? Their life support systems were tailored to the unique personality of the earth that housed them, a testament to a flexibility and intelligence that resonates across millennia. It prompts a reflective question for our own time. In an age of standardized solutions, what might we learn from such deeply contextual, place-specific ingenuity? The air they breathed was a silent language speaking directly to the spirit. In the profound darkness of a sealed city, the quality of the atmosphere was not just a matter of physical health, it was the very fabric of mental resilience. Stagnant, heavy air does more than deplete oxygen, it weighs on the mind. It fosters a creeping sense of lethargy, of confinement that can turn to despair. For a community under siege, cut off from sun and sky, morale was as critical a resource as grain or water. A collective feeling of sluggishness or creeping illness could unravel social bonds faster than any external enemy. The engineers understood this on a human level. Their ventilation systems were, in a very real sense, psychological lifelines. The gentle, consistent flow of fresh air from a distant shaft was a tangible reminder that the world above still existed, that connection was maintained. That cool draft on the face was not just a physical refreshment, it was a message of hope, a proof that their sanctuary was alive and functioning. It combated the oppressive stillness that could make a stone chamber feel like a tomb, replacing it with the subtle, reassuring evidence of a living system. This psychological dimension transformed engineering into a form of communal care. To breathe freely underground was to believe in a future back in the light. This connection between breath and being often found its most profound expression in sacred spaces. In many underground complexes, places of worship and ritual were deliberately positioned near major ventilation shafts or at points where fresh air currents were strongest. This was likely no accident. The sensation of moving air in a ceremonial chamber would have carried deep symbolic power. Across countless cultures, breath is synonymous with spirit, with the divine spark of life itself. In the stillness of a subterranean church or temple, the felt presence of a fresh breeze could be interpreted as something more than physics. It might be experienced as the breath of the divine, a spiritual visitation, or a purification of the space. The very act of drawing a clean, cool breath during a prayer or ritual would have reinforced a fundamental link between the community's physical survival and its spiritual sustenance. The engineers, perhaps in collaboration with spiritual leaders, were effectively weaving a sensory experience into their architecture, using the ventilation system to elevate the atmosphere of their most meaningful gatherings. This fusion of environmental control and sacred practice reveals a holistic world, where technology served the soul as well as the body. Ultimately, the silent, successful operation of these vast air systems became the ultimate symbol of the community's own strength. In a world turned upside down where hostile forces controlled the surface, maintaining a fresh, breathable atmosphere deep within the earth was a continuous, quiet triumph. It was a daily demonstration of order imposed upon chaos, of human ingenuity asserting control over a fundamentally alien environment. Every breath drawn in safety was a vote of confidence in the system, and by extension, in the social order that built and maintained it. The knowledge that clever ancestors had designed this, that skilled masons had carved it, and that everyone had a role in preserving it, forged a powerful collective identity. This shared technological mastery became a bedrock of social stability during crisis. While the world above descended into conflict, the community below could point to the gentle air in their chambers as proof of their resilience, their preparedness, and their right to endure. The ventilation shafts were more than engineering. They were the steady heartbeat of a civilization that refused to be extinguished, a promise carved in stone that as long as they could breathe, they would survive. This constant, silent circulation was powered by more than just stone and temperature. It was powered by life itself. The fourth principle these ancient engineers mastered was perhaps the most ingenious of all. They turned the inhabitants, both human and animal, into active components of the ventilation machine. Every single resident of the underground city became a tiny, living piston in a grand, biological engine. Consider the simple act of walking. Thousands of people moving through the narrow, winding corridors day after day did not just traverse space, they moved air. As a person walks down a tunnel, their body displaces the air in front of them, creating a subtle pressure wave that pushes air ahead. Behind them, a slight vacuum pulls air forward to fill the space. This constant, rhythmic human traffic created a gentle, persistent piston effect throughout the entire network, a collective breath of motion that kept the atmosphere from ever growing completely still. It was a form of crowd-sourced ventilation where the very purpose of the city to house a community directly fueled the system that sustained it. The contribution of animals was even more direct and powerful. The large stables, often located on the lower levels, were not merely storage for essential livestock. They were vital thermal power plants. A single ox or donkey generates a considerable amount of body heat, and its respiration releases both warmth and moisture into the surrounding air. A whole stable full of animals created a significant, localized hotspot deep within the cool rock. This was a masterstroke of environmental design. By placing this concentrated source of biological heat at the bottom of the complex, the engineers supercharged the stack effect. The warm, moist air from the stables would rise powerfully, seeking the cooler upper levels and the exhaust shafts, pulling a steady stream of fresh replacement air down through the intake tunnels with greater force. The animals, simply by existing, by eating and breathing, became the living bellows for the entire city. Some researchers have proposed an even more active role for these animals. There is a compelling theory that certain wider, more robust tunnels, perhaps with distinctive wear patterns on the floors, were not just for occasional movement of herds, but were deliberately used for scheduled ventilation drives. Imagine a practice where, at set intervals, keepers would guide a small herd of sheep or goats through a specific circuit of passageways. The movement of the animals would churn the air dramatically, breaking up stagnant pockets and pushing fresher air into side chambers and dead ends that the passive systems might miss. This would have been a brilliant, low-tech solution to a complex problem, using the herd's instinct to move as a group to perform essential atmospheric maintenance. It transforms the concept of livestock from passive resource to active maintenance crew. This bio-integrated approach represents a pinnacle of sustainable thinking. The city operated as a remarkably closed-loop ecology. The metabolic outputs of its residents, their body heat, their breath, even their movement, were not seen as waste to be managed, but as valuable inputs to be harnessed. The warmth from a cooking fire, the exhalation of a family in their chamber, the steady heat from the stables below, all of it was captured and channeled, becoming the very energy that drove the renewal of their air. This creates a profound image of harmony. The people and animals were not separate from their engineered environment. They were woven into its fabric. Their life processes directly maintained the conditions that allowed life to continue. It challenges our modern separation of living spaces and mechanical systems. For them, the system was alive because they were part of it. This deep integration leads to a final, haunting layer of their legacy, one that speaks not of how they lived, but of the silence they eventually left behind. What happens when the breath of life finally leaves a stone city and the ingenious systems fall still? The very systems that gave life could also invite death. This was the ultimate paradox of the subterranean city, a dilemma carved into every breath its inhabitants took. For the architects, the ventilation network was not just an engineering problem, it was a profound security calculation. Every shaft that opened to the surface was a potential breach, a whispering tunnel that could betray the city's secret location or, worse, become a weapon turned against them. An enemy above could pour smoke down a vent to suffocate the inhabitants, introduce noxious fumes, or even attempt to send small, probing forces into the heart of the refuge. The brilliant airflow that sustained them had to be designed with an equally brilliant defense. The solutions they engineered reveal a mindset that thought in layers of protection, where every feature served a dual purpose of life support and tactical denial. Consider the anatomy of a typical ventilation shaft. Its design was a masterclass in controlled access. While the lower sections within the city might be wide enough for maintenance, the upper reaches, especially the final segment opening to the surface, were often deliberately constricted. Builders would carve these final passages with extreme narrowness, sometimes to a diameter barely wider than a person's arm. This was a physical filter. It allowed air and light to pass freely, but it presented an impassable barrier to any would-be intruder. Even more clever were shafts that incorporated sharp, right-angle turns or serpentine bends just below the surface opening. These twists made it impossible to see down into the city or to shoot projectiles or pour liquids directly into the living spaces below. The air could navigate the labyrinth, but an attack could not. It was architecture as a selective membrane, discerning friend from foe at the molecular level. The most direct security measure, however, was the ability to sever the connection entirely. In many complexes, the surface openings of key shafts were fitted with heavy, meticulously crafted stone caps or plugs. These were not mere rocks, but engineered seals, often with grooved edges that fit into a corresponding lip in the shaft opening. In times of immediate threat, designated guardians could ascend to these points and seal the city off from the world above, transforming a vent into a solid plug of stone. This act would have been a grave decision, trading fresh air for absolute security, a temporary measure to outlast a direct assault at the entrance. It speaks to the precision of their planning that they could, for a critical period, switch their life support system into a dormant, sealed state. The strategy extended to the very placement of these vital openings. Intake vents were rarely, if ever, located near the main fortified entrances. Instead, builders would run air tunnels for astonishing distances, sometimes hundreds of feet, to surface in remote, inconspicuous locations. An intake might emerge in a secluded gully, on a steep cliff face, or amidst a dense thicket of boulders. The goal was camouflage, making these openings indistinguishable from the natural fractures and holes of the rocky landscape. An invading army scouring the area would see only random stone, completely unaware that just beneath their feet, a hidden city was drawing a silent, steady breath from the very ground they stood on. This geographical deception was the first and most elegant line of defense, hiding the system in plain sight. This relentless conflict between openness and isolation, between breadth and barrier, defines the true genius of these underground fortresses. It was not a compromise but a sophisticated integration. The architects did not choose between security and ventilation. They engineered a system where one enabled the other. The need for secrecy dictated the remote, disguised placement of vents, which in turn often improved airflow by tapping into cleaner, more consistent wind currents away from disturbed ground. The need for defense shaped the shaft's tortuous internal geometry, which incidentally helped regulate air pressure and velocity within the city. Every security feature had to be reconciled with the non-negotiable law of survival that people must breathe. This ongoing risk calculus, etched into the rock over generations, produced environments of profound resilience. It forces us to see these spaces not as passive hideouts, but as active, intelligent shields, where the atmosphere itself was a guarded perimeter. The knowledge that built these breathing mountains was never written in stone. It lived in the hands and minds of the master builders, a tradition passed not through scrolls, but through the steady rhythm of apprenticeship. A young mason would not learn from a textbook on fluid dynamics, but by standing beside his teacher, feeling the subtle draft at the mouth of a new tunnel, observing how the smoke from a lamp curled toward a specific fissure. This was engineering as an oral craft, refined over countless generations through a slow accumulation of trial, error, and profound observation. The perfect diameter for a shaft, the ideal slope for an intake tunnel, the precise placement of a stabilizing arch to direct airflow, these were not sudden inventions. They were hard-won secrets, the collective intellectual property of a guild whose blueprint was experience itself. This deep, practical wisdom allowed the craft to travel. As merchants and migrants moved along the ancient trade routes of the Mediterranean and Asia Minor, the core principles of subterranean living migrated with them. A technique perfected in the soft tuff of Cappadocia might be adapted by builders facing the granite of another region, reinterpreted through the lens of local materials and threats. The knowledge was fluid, a toolkit of concepts, not a rigid set of instructions, enabling diverse cultures from North Africa to the Middle East to create their own versions of breathable, hidden worlds. Yet this very strength, its embedding in human skill and speech, became its greatest vulnerability. When the threats that forged these cities finally faded, when communities felt secure enough to return permanently to the surface, the urgent need for this specialized knowledge faded with them. The master builders found no new apprentices. The subtle cues for reading airflow in total darkness, the tricks for disguising a vent as a natural rock formation, the communal protocols for sealing and reopening the city's lungs during a crisis, these nuances were no longer practiced. They were not forgotten overnight, but they slowly evaporated from living memory, becoming stories, then legends, then silence. The engineering marvels themselves were not lost. They were simply buried, waiting under layers of soil and oblivion. For centuries, they were known only as caves or curious holes in the ground, their true purpose and sophistication completely misunderstood. It took the careful, methodical work of modern archaeology to begin piecing the puzzle back together. Researchers had to learn to read the architecture not as rooms but as a system. They mapped air currents with modern instruments, discovering the logic behind every offset doorway and winding corridor. They realized the well was not just a well, and the strange narrow chimney not merely a chimney. Each excavation slowly restored the language of this lost engineering, translating the silent grammar of the stone back into a testament of human ingenuity. This cycle of brilliant innovation and subsequent oblivion adds a haunting layer to these sites. It reminds us that technological sophistication is not a guaranteed, linear march forward in history. A civilization can reach dazzling heights of practical genius, creating systems that sustain thousands, only to have that specific wisdom dissolve back into the earth from which it came. The underground cities stand as monumental evidence that progress is not always cumulative, that peaks of knowledge can be isolated by time and circumstance, waiting centuries for a future age to rediscover and comprehend their silent, breath-filled halls. The silent wisdom of those stone corridors never truly vanished. It simply went dormant, waiting for a new generation to listen. The principles that kept entire cities alive underground are now experiencing a quiet but powerful renaissance in our own modern world, not as forgotten history, but as cutting-edge inspiration for sustainable design. Today's architects and engineers, tasked with building the resilient infrastructure of the future, are looking back to these ancient solutions with a profound sense of recognition. In an era defined by climate challenges and energy scarcity, the passive, elegant intelligence of the past offers a compelling blueprint. The goal is no longer just to build shelters, but to create systems that breathe with minimal cost to the planet, and the answers have been resting beneath our feet for millennia. Consider the vast, humming subterranean realms we now take for granted. Massive data centers, the invisible brains of our digital world, generate immense heat and require perfect climate control. Modern subway networks stretch for miles, moving millions of people through tunnels where air quality is paramount. The designers of these facilities face a strikingly familiar equation. How do you maintain a safe, stable atmosphere deep underground without relying entirely on massive, energy-hungry mechanical systems? The answer increasingly involves looking to passive strategies pioneered in places like Derinkuyu. By intentionally designing access shafts, air plenums, and tunnel geometries to harness the stack effect, modern engineers can significantly reduce the load on powered ventilation. They are, in essence, relearning how to let physics do the heavy lifting, using the Earth's own thermal mass as a giant heat sink to cool server halls or stabilize temperatures in transit corridors, dramatically slashing electricity use and carbon footprints. This is not nostalgia, it is high-performance biomimicry, using ancient geological wisdom to solve contemporary problems. This ancient dialogue with thermal mass has become a cornerstone of modern green building, even on the surface. Today's most advanced sustainable homes and offices are often built with thick walls of rammed earth, adobe, or dense concrete, materials chosen specifically for their ability to absorb heat during the day and release it slowly at night. This is the exact same principle that stabilized temperatures in an underground city, now translated upward. Architects call it passive solar design, but its roots are in the intuitive understanding that the mass of the Earth itself is the most reliable battery for thermal energy. By thoughtfully positioning buildings and selecting materials, we can create structures that require far less active heating and cooling, echoing the ancient goal of achieving comfort through harmony with the environment, not domination over it. The holistic integration seen in ancient cities, where air, water, security, and social space were all part of one system, now finds its echo in the planning of resilient communities and disaster shelters. Modern planners designing refuges for extreme weather events or long-term crises are moving away from isolated solutions. A contemporary resilient shelter is not just a strong room, it is a micro-ecosystem that considers rainwater harvesting, passive ventilation through thermal chimneys, secure but breathable perimeters, and layouts that support community morale. This systems thinking, where every element supports multiple survival functions, is a direct parallel to the ancient mindset that saw a well as both a water source and an air shaft. The lessons are clear. True resilience is not found in a single piece of equipment, but in the intelligent interconnection of all resources. These timeless strategies offer more than just technical blueprints, they provide a philosophical shift. In a world racing toward complex, energy-intensive technological fixes, the ancient models remind us of the power of simplicity, of designing with nature's forces as partners. They prove that some of the most innovative ideas for a sustainable future are not always ahead of us, waiting to be invented, but sometimes behind us, waiting to be remembered. The breath of those hidden cities still moves, not through stone shafts, but through the evolving designs of a world learning that to build for tomorrow, we must sometimes listen to the whispers of a deep and clever past. The silent stones do not give up their secrets easily. To truly understand the breadth of a forgotten city, we must become detectives of the invisible, learning to read the language of empty space and still air. This is where the meticulous science of modern archaeology converges with the echoes of ancient engineering, using tools our ancestors could never have dreamed of to decode the systems they left behind. The first step is seeing the city not as a collection of rooms, but as a single, interconnected organism. Archaeologists now employ three-dimensional laser scanning, a technology that fires millions of precise laser points into every crevice and shaft. This creates a breathtakingly accurate digital twin of the entire complex, a map so detailed it can reveal the subtle slope of a floor designed to guide condensation, or the exact alignment of a ventilation shaft with a distant surface fissure. This digital model becomes the canvas for a remarkable kind of forensic engineering. Using sophisticated software known as computational fluid dynamics, or CFD, researchers can simulate the ancient air itself. They input data about the digital geometry, estimated temperatures from historical climate records, and the known heat output of human bodies and oil lamps. With a click, the software animates the invisible. It shows how air would have flowed on a still summer day versus a windy winter night, revealing which corridors acted as swift arteries and which chambers might have needed supplemental airflow. It allows scientists to test theories, virtually blocking a shaft or opening a sealed door to see how the entire system's pressure would have shifted. This isn't guesswork, it's a rigorous digital reconstruction of a lost environment, letting us witness the engineering logic in motion. The detective work extends to the surface where the landscape holds camouflaged clues. High-resolution drone photography, equipped with thermal and multispectral cameras, scans the rocky terrain from above. What looks like a random scatter of boulders to the human eye can, through these lenses, reveal subtle thermal signatures or vegetation patterns that betray the presence of a buried void below. A hidden intake vent, sealed for centuries, might cool the ground above it differently than the surrounding earth, or cause plants to grow in a distinct linear pattern along its underground path. By correlating these aerial anomalies with the underground digital map, archaeologists can pinpoint the exact, disguised locations where the city once drew its breath from the world above. Perhaps the most elegant evidence comes from simple, precise measurement. Scientists place sensitive sensors throughout the ruins to monitor tiny gradients in temperature and humidity over days, weeks, and seasons. Even in a static, excavated site, these differentials persist, whispering the ghost of the original system. A shaft that was once a major exhaust will still show a minute but consistent upward drift in temperature compared to the surrounding rock. A long, downward-sloping entrance tunnel might remain slightly cooler and damper, tracing the ancient path of incoming air. By meticulously mapping these microclimates, researchers can reverse engineer the ventilation patterns, distinguishing primary airways from secondary passages. This interdisciplinary synthesis, blending the historian's context with the physicist's models and the surveyor's maps, achieves something profound. It allows us to virtually stand in that deep chamber, not as tourists viewing a ruin, but as inhabitants feeling the subtle, life-saving draft on our faces. We can appreciate not just the brute effort of carving a city from rock, but the exquisite precision of its design, the millimeters of slope that made all the difference. The stones are silent, but through this fusion of past and present technology, we can finally hear the whisper of the air that once meant survival, bringing a forgotten world back to life one calculated breath at a time. A city's breath had to change with the seasons. This is the fifth and perhaps most sophisticated principle of their design, seasonal and diurnal adaptation. Their ventilation was not a static, set-and-forget mechanism, but a dynamic, living system that required constant, intelligent adjustment to the rhythms of the world above. The engineers understood that the very forces that powered their airflow could, if left unchecked, work against the comfort and survival of the community. Take the deep cold of winter. This is when the temperature difference between the warm, inhabited caverns and the frigid surface air would be at its most extreme. The stack effect, driven by this powerful thermal contrast, would surge into overdrive. Air would rush in with such force that it could transform the underground refuge into a wind tunnel, stripping away precious warmth, chilling inhabitants to the bone, and making communal spaces unbearable. The solution was not to stop the flow, but to master its intensity. Evidence from various sites suggests the use of primitive but effective dampers. At key intake points, movable covers made of stretched leather, thick woven textiles, or even fitted wooden slabs could be positioned to partially block a shaft's opening. By adjusting this aperture, the keepers of the system could throttle the incoming torrent of cold air down to a gentle, manageable breeze, preserving the life-giving exchange without sacrificing thermal comfort. It was a delicate calibration, a daily negotiation with the weather conducted in total darkness. The rhythm of adjustment was not just seasonal, but daily. As the sun set and surface temperatures plummeted at night, the thermal relationship between the city and the outside world could undergo a subtle but significant shift. In certain configurations, the stack effect could weaken or even temporarily reverse during these hours, as the surface air became colder and denser than the stable air within the rock. This required an intuitive understanding of these nocturnal patterns, perhaps involving the strategic opening of different vents or the temporary sealing of others, to maintain a consistent internal atmosphere while the world above slept. This necessity for active, knowledgeable management points to a critical social innovation, the likely existence of a dedicated societal role. We might call this person the ventilation keeper, a guardian of the invisible. This individual or small group would have possessed specialized, handed-down knowledge. They knew which shaft caught the prevailing wind, which corridor was prone to drafts, and how to read the behavior of smoke from a lamp to diagnose airflow. Their daily rounds would involve checking shafts for blockages, adjusting dampers with the turning seasons, and sealing vents during driving rains or sandstorms. This was not a menial task, but a position of profound trust and responsibility. The health of every person, the preservation of stored food, and the community's collective morale literally rested on their skill. This role embodies the ultimate sophistication of these ancient systems. It shows that the engineering was not just carved in stone, but embedded in culture and social organization. The city did not breathe automatically, it breathed because someone, trained in a deep oral tradition, listened to the whispers of the rock and knew how to answer. But fire was a double-edged sword in the world of stone. It pushed back the darkness and warmed the chill from the rock, yet its byproduct, smoke, introduced a new and dangerous complexity into the carefully balanced atmosphere. Every flickering lamp, every cooking hearth, and every communal fire filled the air with fine particles and gases that could choke a community as surely as stale air ever could. Managing this essential but toxic element became a parallel engineering challenge, a constant dance of containment and expulsion that reveals yet another layer of their sophisticated environmental control. The ventilation shafts were the obvious solution, serving as natural chimneys for the warm, smoky air to escape. Yet simply letting smoke rise through a shared airway was fraught with risk. If a major shaft became the primary exhaust for a cooking area, it could pull that smoke through living quarters on its way out, fouling the air people were trying to breathe. The solution was often a deliberate separation of flows. In some of the more advanced complexes, archaeologists have identified smaller, dedicated smoke channels. These were carved with specific purposes, connecting directly to key hearths, communal kitchens, or lamp-lit workshops. They functioned like targeted exhaust ducts, capturing combustion products at their source and funneling them directly upward and out, bypassing the main living spaces entirely. The surface outlets for these channels were masterpieces of concealment. They might emerge as narrow fissures high on a remote cliff face, disguised within a natural rock chimney, or hidden among a field of boulders. The goal was to allow the smoke to dissipate unseen, its faint wisp blending into the landscape or the haze of the distant horizon. A column of smoke rising from an otherwise barren plain was a beacon, a clear signal of hidden life below. By fragmenting and camouflaging these exhaust points, the engineers protected the city's greatest secret, its very existence, every time a meal was cooked or a lamp was lit. The management extended to the fire itself. The design of hearths was not left to chance. Many were shallow, stone-lined pits positioned with clear sight lines to an overhead vent or integrated into a wall that backed onto a dedicated smoke channel. The placement encouraged the smoke to be drawn upward immediately, rather than rolling out into the room. The choice of fuel was also a calculated decision. Where possible, communities would favor fast-burning, resin-poor woods that produced less thick, lingering smoke. The gathering and storing of specific fuels became another thread in the tapestry of survival, a quiet logistical effort that supported the larger engineering system. This holistic approach to combustion reveals an acute awareness of health and safety that feels remarkably modern. They were not merely avoiding discomfort, they were actively managing air quality by removing specific pollutants. Inhaling smoke over long periods leads to respiratory illness, eye irritation, and long-term health decline, a danger that would have been readily apparent even without modern medicine. By designing systems to remove this hazard, they were practicing a form of preventative health care, engineering their environment to protect the physical well-being of every man, woman, and child in the depths. This turns the simple act of lighting a fire into a profound statement of care. It demonstrates that their concept of a breathable city was not just about the presence of oxygen, but about the absence of poison. The air had to be fresh, and it also had to be clean. In solving the puzzle of smoke, they acknowledged that the greatest threats to a hidden civilization were often slow and silent, emerging not from outside enemies, but from the very tools they relied on to live. This intricate balance between necessity and danger, between light and toxicity, forces us to see these spaces not as dark holes, but as carefully tuned environments where every spark was both a promise of life and a problem to be solved. The steady whisper from a stone wall was more than just physics, it was a voice. For the people who lived within these breathing mountains, the invisible currents that sustained them would have felt deeply mysterious, even animate. In a world lit by flickering lamplight, where the only sounds were echoes and the only motion was the gentle, inexplicable draft on your cheek, the line between engineering and enchantment would have blurred completely. This profound, daily experience of the living rock did not fade with the last inhabitant. It seeped into the stories they told, transforming clever design into cultural memory. Across the regions that housed these underground worlds, from the high plateaus of Turkey to the rugged landscapes of Iran, a rich tapestry of folklore emerged, speaking not of ventilation shafts, but of earth breaths and cave spirits. These were not mere fairy tales, they were the mythological echo of a very real, life-saving technology, a way for the human mind to give form and meaning to a force it could feel but not see. In countless local legends, deep caves and fissures are described as the nostrils or mouths of the earth itself. Stories tell of sudden, powerful gusts rushing from dark openings, attributed to the slumbering breath of a giant buried within the mountain or the sigh of a geological deity. A cool wind issuing from a crack in a sun-baked hillside was not a thermodynamic event. It was a sign, a communication from the world below. This mythological framework provided a complete and satisfying explanation for a phenomenon that would have been utterly baffling without an understanding of air pressure and thermal dynamics. Why does the air move in this dead-end tunnel? Because the spirit of the place is passing through. What causes that low moan in the deepest chamber? It is the mountain dreaming. These narratives transformed a potentially frightening or confusing experience, the sensation of an unseen force in total darkness, into something knowable and integrated into their cosmology. The engineering became personified, its functions ascribed to conscious, if capricious, beings. The folklore often served a vital practical purpose as well, encoding survival knowledge in the guise of superstition. A tale warning children not to play near a certain crevice because a wind spirit would steal them away might have been rooted in the very real danger of a deep, disguised ventilation shaft. A story about a benevolent cave spirit whose breath brought health, but whose anger could bring sickness, could reflect the observable truth that clean, moving air sustained life, while stagnant, foul air led to illness. In this way, mythology acted as a protective and instructional layer over the technology, ensuring that respect for the system was maintained across generations, even as the precise reasons for its construction faded from common memory. The sacredness attributed to certain caves or springs was frequently tied to the quality of the air within them, places where the earth's breath was felt to be particularly fresh or powerful, likely indicating a site with exceptional natural ventilation. This beautiful intertwining of stone and story offers us a crucial insight. It reminds us that for ancient cultures, technology and spirituality were not opposing realms, but complementary ways of understanding and interacting with a mysterious world. The ventilation system was not just a mechanical achievement, it was a relational one. By attributing agency to the winds within the rock, the people acknowledged their dependence on and connection to their environment in the most profound way possible. They were not masters imposing order upon a passive earth. They were inhabitants in dialogue with a living, breathing entity. This perspective enriched their daily reality, turning the simple, life-saving act of drawing a breath into a moment of potential communion with something greater than themselves. What we, with our sensors and simulations, analyze as a brilliant feat of environmental engineering, they experienced as a continuous, whispered conversation with the mountain that housed them. The myths were not a sign of ignorance, but a testament to the deep human need to weave narrative into experience, to find the story within the stone. In listening to these old tales of earth breaths and tunnel spirits, we are not just hearing fantasy, we are overhearing the echo of a people trying to explain the most vital magic they knew, the silent, moving air that meant they could call the darkness home. Even with our advanced tools and digital reconstructions, the silent cities guard stubborn mysteries. How did ancient engineers, without the language of calculus or fluid dynamics, arrive at the perfect diameter for a ventilation shaft? They possessed no textbooks on air pressure, no instruments to measure airflow velocity. Their calculations were embodied, learned through generations of watching how smoke curled in a new tunnel or feeling the strength of a draft at a tunnel's mouth. The precision we admire was likely born from an immense library of lived experience, a slow, collective refinement where a design that worked was repeated and one that failed was quietly abandoned. This trial and error, conducted over centuries, resulted in geometries that our software now confirms as optimal, yet the path to that knowledge remains beautifully opaque, a testament to human intuition honed by necessity. This leads to a darker, more haunting line of inquiry. In all those centuries of occupation, were there ever catastrophic failures? The systems were brilliant, but they were not infallible. A sudden rockfall sealing a primary intake shaft, a seasonal flood pouring into an exhaust channel, or a prolonged inversion on the surface that stalled the stack effect. Any of these could have triggered a slow, suffocating crisis deep below. While no archaeological evidence points to a single mass tragedy, the potential for localized disasters must have been a constant, unspoken fear. The consequences of such an event would have been profound, reshaping social protocols, inspiring new safety innovations, and likely giving rise to cautionary tales and rituals meant to appease the spirits of the air. The very absence of clear evidence for such events may be the greatest testament to the system's overall reliability and the rigorous, watchful maintenance that upheld it. Beyond passive design, some researchers speculate about active interventions. Could simple machines have assisted the natural airflow? Theories suggest the possible use of water-powered devices, where a channeled underground stream turned a paddle wheel connected to a primitive fan or bellows. Others imagine large leather bellows operated by hand in keyed chambers to push air into dead-end spaces during periods of low natural flow. While no physical remnants of such devices have been conclusively found in these early contexts, the idea is compelling. It represents a bridge between purely passive design and mechanical assistance, a hint that the keepers of these systems may have had tools to correct and perfect the breath of their city when nature's own rhythms fell short. Another frontier of speculation lies in the invisible biological world. What role did plant life or fungi play in the deep chambers? While no crops could grow in the total darkness, certain resilient mosses or fungi might have colonized areas near water seepage or where faint, reflected light crept down a shaft. Some microorganisms consume carbon dioxide. Could the inhabitants have inadvertently cultivated such species, creating a subtle, living supplement to their air renewal? Conversely, could harmful molds or spores have flourished in poorly ventilated corners, presenting a hidden health hazard? These questions push our investigation from architecture into the realm of paleoecology, wondering if the ancient engineers managed not just physics, but a simple, symbiotic biology they scarcely understood. These lingering gaps in our knowledge are not failures of research, but invitations. They are what keep the story alive, transforming it from a solved puzzle into an ongoing conversation. Each unanswered question is a door left ajar, inviting professional archaeologists with new sensing technologies, historians re-examining obscure texts, and even passionate amateurs who might notice a peculiar pattern in a satellite image or a local legend that hints at a forgotten technique. The full story of subterranean survival is still being written, with each generation bringing new tools and perspectives to listen once more to the whispers in the stone. The principles of breathing stone were not confined to a single culture or continent. From the sun-baked deserts of Jordan to the wind-sculpted plateaus of China, human communities facing the same stark equation of subterranean survival arrived at eerily similar answers. This is a story of convergent innovation where isolated cultures, separated by vast oceans and millennia, independently discovered how to make the earth itself inhale and exhale. The famous rock-cut city of Petra, for instance, is renowned for its ornate facades, but its true genius often lies hidden in the ground. The Nabateans were masters of water management in an arid land, carving sophisticated channel systems known as qanats to guide precious water from distant sources. Yet these tunnels served a dual purpose. As water flowed through the cool, underground conduits, it created a natural airflow alongside it. The movement of the water helped pull fresh air through the network, while the constant evaporation from the channel's surface cooled and humidified the air in adjacent chambers and storage rooms. A qanat was not just a pipeline, it was an integrated life support system, delivering both liquid and atmospheric nourishment to the city. Half a world away, on the vast lowest plateau of China, people confronted a different geological canvas. Here, the soil was a thick, compacted wind-blown dust, soft enough to carve yet stable enough to hold vertical walls. Families built their homes not on the land, but within it, creating sprawling underground courtyard complexes. The central innovation was the skywell, a large, open rectangular shaft sunk straight down from the surface into the heart of the dwelling. This was more than a light shaft, it was a brilliant atmospheric engine. The open skywell acted as a giant chimney, harnessing the stack effect with magnificent efficiency. Warm air from the living quarters would rise and escape out the top, while cooler, fresh air was drawn in through the main entrance tunnel, which was always cleverly positioned at a lower level. The design created a continuous, gentle circulation, pulling air through every room arranged around the sunken courtyard. It was ventilation through architecture, turning the home itself into a vessel designed to catch the breeze. Even in the prehistoric temples beneath the Mediterranean island of Malta, known as hypogeums, we find the whisper of managed air. These deep, labyrinthine ceremonial spaces, carved over 5,000 years ago, show evidence of carefully planned openings. Shafts were carved not just for light, but to create specific air currents, perhaps to keep torch smoke from pooling in sacred chambers, or to maintain a fresh atmosphere for gatherings that lasted days. While their exact purpose is layered in mystery, the intentional design for airflow is clear. They understood that to descend into the earth for profound purposes required ensuring that the space remained breathable, that the connection to the world above was maintained, even symbolically, through the movement of air. This global recurrence is profoundly telling. It means that the solutions were not the guarded secret of one brilliant civilization, but rather emergent properties of a universal human ingenuity when pressed by necessity. When the problem is absolute, when the need for fresh air becomes synonymous with the need to persist, the human mind, observing the same natural laws of rising heat and moving air, will reliably chart a similar course. It reveals a shared intellectual heritage not of borrowed ideas but of parallel discovery. The physics of warmth and pressure, the biology of human need, these are constants. From the volcanic rock of Turkey to the lowest soil of China, different hands working different stone all learn to listen to the same silent teacher, the fundamental behavior of the atmosphere itself. This convergence suggests something beautiful about our species, that our cleverness is not random, but a directed force that, when faced with a fundamental challenge, tends to spiral toward elegance and efficiency. It makes you wonder what other universal human solutions are waiting to be recognized, hidden in the adapted forms of distant, unconnected cultures. A breath drawn today in those silent halls moves through stone shaped by a forgotten science of materials. The astonishing endurance of these ventilation systems, standing strong for over a millennium, speaks to a choice far deeper than simple excavation. It was a dialogue with the very substance of the earth, a selection process where the wrong rock could mean collapse, and the right mixture could ensure a city's breath for generations. Stability was the non-negotiable first principle. Builders sought out specific geological formations, layers of rock that offered a perfect balance between workability and permanence. In Cappadocia, the volcanic tuff was ideal, firm enough to hold precise shapes yet soft enough to carve without shattering. In harder granite regions, they followed natural fault lines and seams, using the stone's own weaknesses as a guide to avoid the immense labor of cutting against the grain. This was not random digging, it was a form of geological prospecting, reading the land to find the strata that would become a reliable, breathing wall. The interior finish of these airways was often as considered as their placement. Simply hacking a hole through rock leaves a rough, jagged surface full of friction, which disrupts smooth airflow. In some sophisticated sites, archaeologists have found evidence of shafts lined with fitted ceramic pipes or coated with a thin, hard plaster. This was a stroke of aerodynamic genius. By creating a smooth, uniform interior surface, the engineers dramatically reduced turbulence and resistance, allowing air to travel farther and faster with less energy lost. It transformed a crude tunnel into a refined duct, a subtle upgrade that could mean the difference between adequate ventilation and optimal airflow for the deepest chambers. Every seal was a calculated compromise. The heavy stone plugs or dampers used to close vents during an attack could not be permanent. They had to create an airtight barrier when needed, yet be removable by human hands when the danger passed. The mortars and packing materials used around these movable components had to be durable enough to withstand pressure changes and minor moisture, yet brittle enough to be chipped away without destroying the finely carved ceiling lip. This likely involved mixtures of local clays, crushed limestone, ash, and even organic binders, recipes perfected through experimentation to achieve just the right balance between security and accessibility. Each material choice was a local solution, a testament to profound practical knowledge. Builders did not import exotic substances, they became experts in their immediate environment. They knew which local clay fired into a waterproof ceramic, which mineral made a plaster that resisted cracking, which tree produced a resin that could seal a joint. This hyper-local material science meant every underground city was, in a sense, unique, its ventilation system crafted from the chemistry of its own landscape. The longevity we witness today is the final proof of their mastery. It shows they understood that engineering a breathable world was not just about carving space, but about partnering with materials that would hold that space open against the immense, patient pressure of the earth itself. They built for the long siege, not knowing it would last 1,000 years, yet their choices in stone and mortar ensured that when we finally rediscovered these places, we would not find tombs but time capsules of air still waiting in the dark. The silence of the deep earth was never truly silent. In the profound stillness of a sealed city, where the only light came from flickering lamps and the only sounds were the murmur of voices and the scrape of daily life, the air itself began to speak. An often overlooked sixth principle of their design was not carved in stone, but heard in the darkness, the use of acoustics as a vital tool for monitoring the invisible. In a world without gauges or sensors, the human ear became the primary instrument for diagnosing the health of their life support system. The gentle whistle of air moving through a narrow shaft, the low hum at a tunnel junction, the subtle hiss from a distant vent, these were not random noises. They were the steady, audible heartbeat of the city, a constant acoustic signature that the keepers learned to recognize. A change in that signature, a whistle that grew faint or a hum that rose in pitch, was an immediate alarm. It could signal a partial blockage from a rockfall, a shift in the surface wind altering the pressure balance, or even the subtle tell of a camouflaged vent being discovered and tampered with above. In the total absence of visual cues, this auditory layer of engineering transformed every member of the community into a passive monitor. You did not need to be a master builder to notice when the familiar sound of moving air from the corner vent had stopped. You only needed to listen to the new, wrong silence. This acoustic intelligence extended to the very shape of their communal spaces. Large chambers with poor airflow did more than grow stale. They developed oppressive acoustic qualities. Stagnant, humid air absorbs sound differently, making voices sound muffled and distant, while certain geometries could create disorienting echoes that fractured conversation and made coordinated activity difficult. The architects likely considered this. By ensuring a steady flow of fresh air through these spaces, they were also preserving acoustic clarity. Moving air, while it might add a soft background whisper, prevents the dampening, dead quality of stagnant atmosphere. A well-ventilated hall allowed voices to carry, instructions to be heard, and songs or prayers to resonate clearly, supporting both practical communication and communal morale. This sensory layer of design reveals a breathtaking holistic awareness. The engineers were not just solving for oxygen and carbon dioxide, they were designing for human perception itself. They created a system that could be felt on the skin as a draft and heard in the ear as a specific tone. A keeper walking the corridors at night might not need to see every shaft. He could simply listen to the chorus of winds, diagnosing the city's respiratory health through a symphony of whispers. This multi-sensory approach turned environmental management into an embodied practice, a continuous, quiet dialogue between the people and the breathing stone around them. It prompts a reflective thought. In our own world of silent digital monitors and blinking lights, what vital signals from our own environments have we simply forgotten how to hear? The engineered breath of a city can last only as long as the people who remember its rhythm. The great subterranean refuges were not abandoned in a single, catastrophic exodus, but through a slow, quiet forgetting. The very threats that had carved them into being began to recede. Shifts in political power created larger, more stable surface empires where fortified towns offered sufficient security. Advances in warfare may have rendered a hidden city less of an absolute sanctuary. Perhaps most decisively, subtle changes in regional climate patterns made the surface lands more fertile and hospitable for longer periods, tilting the balance of risk and reward toward life under the open sky. The communities that had once descended en masse for safety began to stay above ground for seasons, then years, then generations. The maintenance cycles, so vital to the city's invisible lungs, stretched thin and finally broke. Without the careful, seasonal clearing of vents by human hands, the silent work of the earth began. Wind-blown dust and fine silt, season after season, drifted into the open shafts. Minor rockfalls, unchecked by repair, partially blocked tunnels. Leaf litter and soil accumulated, slowly choking the engineered airways. The great stack effect, dependent on clear pathways, grew faint. The gentle drafts that had once whispered through corridors stilled into a profound, dry silence. The cities did not die violently. They simply fell into a deep, geological sleep, their breath slowing until it stopped altogether. Yet in this seeming end lay the beginning of their modern legacy. That very abandonment became an act of accidental preservation. Sealed off from the elements and from human disturbance, the interiors entered a state of remarkable stasis. The air, now still and devoid of moisture-laden human breath, became incredibly dry. This arid environment proved to be a perfect conservator. Wooden tools, textile fragments, and even food remains that would have rotted in a damp cave or on the surface were slowly desiccated, mummified by the unchanging atmosphere. Elaborate carvings on walls and pillars were spared the weathering of flowing water or cyclical freezing and thawing. The intricate markings left by the builders, the soot patterns from lamps that trace ancient air currents on ceilings, all were frozen in time. It was this sealed, silent tomb-like quality that protected the cities as time capsules. When archaeologists first began to carefully excavate sites like Derinkuyu, they were not entering a collapsed ruin, but opening a perfectly preserved snapshot. They found millstones left beside grain storage pits as if the keeper would return at any moment. They could trace the soot from a last lit lamp up a wall and into a dark vent. The engineering was not a theory to be pieced together from fragments. It was a complete, dormant system waiting to be awakened by a gust of fresh air from a modern tunnel. The abandonment that stilled the breath of these places is precisely what allowed their stories to survive intact for us to hear. Their greatest engineering triumph, the creation of a breathable world, was ultimately safeguarded by the world holding its own breath for centuries. This strange, quiet fate invites a deeper reflection, not on how they lived, but on the legacy they left in the stillness. What does the silent, perfect preservation of a community's most vital systems tell us about the things we build to last and the unexpected ways they endure? The legacy of these stone lungs is a testament to a different kind of intelligence. Our journey through the engineered atmospheres of ancient underground cities reveals a breathtaking legacy of innovation, one where survival was not won through domination, but through a deep, listening harmony with natural forces. These builders did not invent new physics, they became fluent in its silent language. They understood that warmth rises, that wind seeks a path, and that the earth itself holds a steady temperature. Their genius was in the invitation, in carving the channels that allowed these timeless principles to do the work of preservation. From the precise physics of air pressure to the subtle psychology of communal space, every carved corner and offset doorway served a unified purpose, creating environments where communities could not just endure, but truly live in the profound darkness. This represents a holistic pinnacle of pre-industrial engineering, a seamless fusion of environmental science, social planning, and architectural artistry. It was technology in service of life in its most fundamental form. These silent cities stand as a quiet challenge to our modern assumptions about technological progress. We often equate advancement with complexity, with power consumption and digital precision. Yet here, in the cool dark, we find systems of stunning elegance that required zero fuel, emitted no waste, and operated for centuries on the logic of nature itself. They achieved a level of sustainable, resilient design that our own world now urgently seeks to rediscover. The lessons are carved in the rock, waiting to be read. They teach us about designing with the environment, not against it. They show the power of passive systems that leverage natural differentials, of materials chosen for their innate properties, and of planning that considers every resource as part of an interconnected web. In an age of climate uncertainty and energy transition, this ancient wisdom feels not outdated but remarkably prescient. As we face our own environmental challenges, from designing energy-efficient buildings to planning resilient communities, perhaps we can look to these subterranean marvels for a profound kind of inspiration. They remind us that the most elegant solutions are often those that work with the grain of the world, that the quest for fresh air, both literal and metaphorical, has always driven human ingenuity to its greatest heights. It is a quest that continues today, in every lab seeking cleaner energy and in every architect drawing a building meant to breathe. The echoes of those ancient drafts still whisper, asking us to remember that true innovation is not always about creating something new, but about understanding with deep humility and cleverness the timeless systems that have always sustained life. Which of these ancient solutions, from the biological bellows of animal stables to the acoustic monitoring of silent shafts, amazed you the most? Share your thoughts in the comments below and subscribe to delve deeper into the forgotten marvels and enduring mysteries of our shared past. The stone cities are no longer relics but blueprints for a future we are only beginning to imagine. As humanity's gaze turns outward to the stars and inward to the pressing needs of our own planet, the concept of building beneath the surface is shifting from ancient history to urgent possibility. The challenges of establishing a habitat on the Moon or Mars are, in their essence, the same challenges faced by the builders of Derinkuyu, only magnified by the void of space. There is no breathable atmosphere, no liquid water on the surface, and the temperature extremes are lethal. To survive, we must create a completely sealed, self-sustaining bubble of life, a task that makes an underground city on Earth look almost simple by comparison. And yet, the core principles remain identical: the need to recycle every molecule of air and water, to use thermal mass for temperature stability, and to design spaces that support both physical health and human spirit over the long term. Modern engineers planning lunar bases are actively studying these very concepts, designing habitats that use regolith, the Moon's soil, as a radiation shield and thermal buffer, much like ancient builders used volcanic tuff. They are planning closed-loop life support systems where plants help replenish oxygen and scrub carbon dioxide, an advanced echo of the ancient understanding that living systems are part of the environmental solution. In looking to the stars, we are being forced to rediscover the most fundamental truths of living within a hostile environment, truths our ancestors carved into rock millennia ago. Their solutions were born of necessity, not of abstract theory, and that gives them a powerful, tested validity. They represent a library of low-tech, high-intelligence strategies for making an uninhabitable space livable. This ancient wisdom is not a curiosity. It is a field guide for our own species' next great migration, whether that migration is vertical, down into the Earth to conserve energy and space, or horizontal, across the cosmic sea to new worlds. The whispering shafts and clever chambers of the past are speaking directly to the architects of our future, offering a timeless lesson in resilience, written in the universal language of survival.